Hello and welcome to the fourth video of my JetCar project mini-series. This one is about the data preparation for the training. The JetBot had a Jupyter notebook for the data collection. There's a live stream image on the left and you would have to click on the steering direction to take a snapshot. That was stored under the subfolder dataset XY. You could then train directly on the Jetson Nano on the stored dataset. As shown in the first video, the JetBot would then follow the street markings after the training. But this method was not sufficient for the JetCar. NVIDIA provides the DeepStream SDK. I downloaded it and tried it out on the Jetson Nano board. And the results are impressive. The example demonstrates not only how persons, bikes and cars are labeled in real time, but also that the make of the car can be recognized. It is definitely something to check out more. But for this project, I decided to go with image segmentation. When I went through the Tensorflow examples, I also tried out this one. The segmentation creates a mask output from the input image with the same size. In essence, each output pixel is a classification output from the input context. The architecture is called UNet, where the input is first sampled down and then up again, with some additional cross connections. In the cat and dog example, the output is simply a mask with three possible values for each pixel: animal, outline and background. That gave me some ideas. You just have to create a mask for each input image with the wanted classification value for each pixel and train the model on that. Back to the street map I made. Now I just needed to record images from the JetCar camera and then somehow create a mask for each image with the classification output I wanted to see. In the previous video, I already mentioned the recording notebook. So I placed the car on the map at many different locations to take snapshots. The images are taken with much higher resolution than needed, so I can downsample after zooming or rotating later. Then I wrote a quick application to create the mask needed. Source code and executable can be found in the GitHub repository under the name Image Segmenter. It shows the original image on the left and the resulting mask overlaid on the camera image on the right. Let's see how it works. The combo box under the left image contains the list of classification objects to choose from. After selection, you simply outline the area with a polygon. For instance, here we start with the white line to the right. It's no problem if it's not perfect. You can always finish the polygon and then edit it. With the mouse wheel, you can zoom in and out and look at the details. When you need more points, just click on the polygon line and a new point will be inserted right there. You can move it on the correct place and check the results on the right side. You can also delete any point by right-clicking on it. Continue until it looks good. When the cursor is close to any edge, the point will snap to the edge, which I found easier to work with than trying to place it directly at the edge. There's a checkbox to turn it off when needed. Now the outlining will have to be repeated again and again for each classification in this scene, which is the most boring part of the machine learning. When it comes to dashed lines, our brains easily abstract this case to tell us that these bunch of dashes are actually a continuous line with a pattern. The interesting part of machine learning is that you can also mark a dashed line as a continuous line for the training, and it will result in a continuous line in the inferred mask later. So let's mark it here as one line with the classification as a yellow dashed line. Finally, we mark the lane in our driving direction and the opposite one as wrong direction lane. All classes have a draw order property, so the lines will be drawn over the lane, for instance. With this, it's much easier to outline the lanes just in the middle of the lines, and it will still come out correct. This draw order can be checked in the application settings form. All classes are listed here with their draw order and their caller used in the GUI. There are more settings to explore, for instance the directories and more. But let's demonstrate some more examples. Here's a kind of an on-ramp with an arrow, the yield text and the yield line. Let's go through this the same way as before. First the shoulder lines. Then the yield text. Then the right turn only arrow. And the lanes. And don't forget the yield line and the dashed line. Let's talk now about data augmentation. The moving car will not always see the same scene in the exact same way. It will be seen from further away or closer. It might be seen at different angles depending on the car's steering and with different light levels. We could take more images under different conditions and mark them all the same way. Or we artificially create different versions of the same scene, thus multiplying the number of training images. There's an augmentation panel that can be checked out to try different parameters. We can zoom in, and tilt. One way or the other. We can change the brightness, or the contrast. Not all values and combinations are helpful, but it gives an idea about the possibilities. If we go back to the settings form, there's that area on the right side for the image augmentation. I found it best to restrict some of the possibilities. For instance, zoom and tilt should be only used together, because it would create black corners otherwise. Similarly, brightness and contrast are better handled exclusive. The checkboxes are checked by default, but can be unchecked if wanted. Below are the fields for entering multiple values for each parameter. The code handles all of them in for loops. The outer loop enumerates through the zoom. The next inner loop handles the tilts, the next inner loop, the brightness, and so on. You can imagine that you can easily generate several thousand datasets from 100 marked images. That has to be kept in mind not to overdo it. When you're done marking all your input images, you can start the dataset generation. There will be one more confirmation required before it will be busy creating the output data, going through all those combinations. The screen will now show all the generated variations, which I cut off here. Just the last example of making the system see things that are not exactly there. At an intersection, we will know how to stay in our lane, even if there's no marking on the street. I experimented with multi-lanes and found that you can mark invisible lines and train with that. It was surprising that the inference created these non-existing lines in the mask. They were not perfect, but good enough for the car to find a way. After the application is done with the data generation, you can check the folders to see all output images and their masks. Since the masks only contain the class numbers, which are 0 to maximum low 20s, depending on the maximum number of classes, these masks appear all black here. Keep in mind that white is represented as 255. One last word about the data format the information for each image is stored. Everything is stored in XML files as commonly used. You can open these files with any text editor. My preference is Notepad++. You can see each polygon with all their point coordinates in floating point format, normalized to the image width and height. The dataset can now be zipped up to be used for the model training. That's the end for this video. Thank you for watching. I hope you enjoyed it and got you interested in watching the next one. And feel free to click the like button. Goodbye.